Welcome, everyone, to Wednesday Night at the Lab. I'm Tom Zinnon. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Haley Vlock. She's a professor here in the Department of Educational Psychology in our School of Education. She was born in Portland, Oregon, and went to high school at Mountain View High School in Bend, Oregon. And then she went to Carnegie Mellon University in Pittsburgh and studied business administration and psychology. Then she moved back west to go to the University of California at Los Angeles for her master's degree and PhD, both of which in psychology. Tonight, she's going to be talking with us about forgetting, what it is, and how it helps us remember. Pretty fascinating topic, a paradox. Please join me in welcoming Haley Vlock to Wednesday Night at the Lab.
Thanks for that introduction. I'm very excited to be here and to speak with you all about some of the work that we've been doing in my lab. I'm director of the Learning, Cognition, and Development Lab. And in my lab, we're really interested in how people think and learn. We spend a lot of time thinking and learning about thinking and learning. And in particular, we're interested in cognitive development. That is, how does thinking change across the lifespan? We're particularly interested in thinking and learning during childhood, but we also study adults as well. And we spend a lot of our time thinking about memory and memory changes and how those changes in memory might contribute to our thinking and learning. And we're really interested in memory for a number of reasons. So the first reason is that it's theoretically very interesting. Like, how does memory work? We take in a seemingly infinite amount of information from the world and somehow manage to encode that information, store it, and then retrieve it later when we need it. And so that process is still a mystery and is very motivating to study, that just coming up with a theory of how memory works. Memory is also practically very important for many reasons. So first, it's important to our day-to-day functioning. So for instance, when we're going to the grocery store, we need to remember the things on our shopping list. And we often think in our mind, do I need more milk? And you have to remember whether or not you have milk in the fridge currently. There's also many ways in which memory can be applied into training, educational, and health interventions. Memory is at the core of allowing us to think and learn, as we will discuss more today. And so there are numerous applications. But on a more sort of spiritual or emotional level, memory is fascinating because it's what defines us. In other words, we are our memories. When we create our sense of self, we think back to all of our experiences, and what those experiences are the memories that we've stored in our brain. So memory truly serves as the foundation of the self. So there are many, many reasons to study memory. One thing that is very interesting to most people who are learning about memory for the first time is that remembering is not the most common part of memory, but instead the most ubiquitous process in memory is the fact that we forget. Today, what I'm going to do is I'm going to first provide an overview on forgetting. What is it and what do we know about forgetting? After that brief introduction, we're going to dive into talking about forgetting helping us to learn. And this is counterintuitive, as we will discuss, because normally we characterize forgetting as a process that deters memory. And then finally, I'll end with some concluding thoughts about where we can go and how we can think about forgetting in our day-to-day lives. So first, let's dive in. Let's talk about what forgetting is and how scientists think about forgetting when we study it from a scientific perspective. Forgetting is operationally defined as the declining ability to retrieve information across time. And what you can see here in this image is on the x-axis is time, so number of days or a month. And then on the y-axis, you see this equation. And this equation is called a saving score. And you can think about this as the percent that is recalled across time. And what you can see is that the nature of forgetting is such that soon after learning something, we have pretty good memory for it. But over time, that ability to retrieve the memory declines. And it declines according to what we call a forgetting curve. Okay? So the curve is fast changing at first, but then over time slows down and gives sort of a U shape to the curve. And we've been studying this process for a considerable amount of time, dating back to the late 1800s at the birth of psychological science. So because forgetting has been such a well-studied process, we know some things about it. And I'm going to give you a brief overview of what we know. So first, we know that we forget across the lifespan. So forgetting happens in young infants, in adulthood, and in older adulthood. In other words, every stage of life we observe forgetting. The next thing that we know about forgetting is that forgetting happens across tasks and time scales. And it's a very predictable pattern. And in fact, that pattern is what I just showed you earlier, the forgetting curve. Now in this figure, what I have here are two different graphs. On the left side of the screen, you'll see that the x-axis indicates time as a matter of seconds. However, on the right side, there's a different dimension of time, which is years, like 0 to 50 years in particular. And then on the y-axis for both graphs is the percent correct. So that's the percentage remembered. And what we can see is regardless of whether or not the time scale is a matter of seconds, as such in the left graph, or a matter of years, such as what we see on the right graph, we see the exact same pattern, that forgetting curve. Now, for those of you that are mathematical buffs, what you can see is that what is charted here is a power function. That's that equation at the top of the graphs. And indeed, forgetting follows a power function with a high degree of fit. So those R squared values are what you're seeing is like the percentage at which the power function can account for the data that we observe via forgetting. And one thing that is fascinating about forgetting is that it's one of the things that we can mathematically model the best of human cognition. Indeed, capturing about 88 or 90% of the variance is very high. And so forgetting is very predictable across timescales, but also across tasks. We see these similar forgetting curves across tasks. The next thing we know about forgetting is that we can observe forgetting on multiple levels of analysis. In other words, we see forgetting on the level of an individual neuron in our brain, but we can also observe forgetting in complex human behaviors, such as those day-to-day functions that we engage in, especially more complex things like learning new concepts in the classroom. So we're seeing forgetting at multiple levels of our being as humans. We also know that we're not alone. Humans are not the only ones that forget. We can observe forgetting in other species, even organisms that don't have our nervous system. So for example, in very simple organisms that only have a matter of cells, we observe that those cells will forget. So forgetting is not something that's specific to the human experience or our nervous systems. It's much more widespread across organisms. Okay, so at this point, what you are probably thinking is that, wow, so what you're telling me is that we're forgetting everything all the time. And that's right. We are forgetting everything all the time. It is predictable and it's inevitable. So why does this happen? Why is this happening to us all the time in a predictable manner? Well, the truth is that we don't know. It's a scientific mystery. We don't know what causes forgetting. But currently, there are two primary theories about why it is that we forget. The first collection of theories focus on interference. In other words, these theories posit that because we're continually acquiring more and more information, that new information blocks us from retrieving the old information in our mind and brain. So if we weren't to learn anything new, we wouldn't forget, is essentially what they're arguing. However, there's a different collection of theories that center on time and the properties of the universe with regards to energy. So, according to these theories, the reason that we forget is that energy passes across biological membranes according to this power function that you've seen earlier. In other words, the forgetting curve. And because of that, we observe forgetting at different units of analysis, like a single cell, but also that scales up to complex human behavior as well. Now, one issue is that we can't control for time and energy. In other words, we can't put people in a vacuum where they're not experiencing time in order to understand whether it's truly interference or time. Moreover, we can't control time when we're doing interference studies. So with additional learning comes additional time. And so the reason that it's a mystery, like, is it interference or is it something about the properties of the universe? We just may never know because we can't put ourselves in a vacuum in order to control these two variables. So the debate rages on, but we're pretty sure that it's either interference, time, or some combination of the two. Okay, so that was the overview of forgetting, what it is and what we know about it. Now I'd like to move on and I'd like to tell you more about why forgetting is actually a good thing. Because at this point, you might be wondering, well, if it's inevitable, predictable, and going to prevent us from remembering things, it must be bad. Well, it turns out that that's not the case. Forgetting can be used to help us remember. So, if forgetting is inevitable, how do we remember? Well, this has been a central research question for many years. And what researchers have discovered are that certain learning environments or conditions of the environment can actually improve our memory. They can help us to retrieve information. One of the most well-studied conditions of the learning environment is called spaced learning. And what scientists have observed is that when we distribute learning events across time, people have better memory for that information compared to it being masked in immediate succession. So here's a real life example of that. Imagine that you are studying for a test. You have one or two options. You could cram the night before and just cram right up until the test. Well, that behavior would be studying in immediate succession. We would call that masked learning. The other option is to distribute your learning during the week and study a little bit every day. So you might study a little bit on Monday, a little bit on Tuesday, a little bit on Wednesday, and so on and so forth, building up to the test. And what you may experience if you cram is that you do okay on the test, you do well enough. But a few days later, you might say, wow, I don't remember anything from the test that I took earlier in the week. However, if you had distributed your learning or spaced it out across time, you would probably experience more memory for what you studied for. In other words, you'd actually remember what you were studying. And that's a real life example of how spaced learning promotes memory to a greater degree than masked learning. In the lab, scientists do this kind of work using word lists. What they do is they present words to participants one at a time. So what you're seeing here on this list is a series of words. And what you'll notice is some of the words, like the word cat, are presented in immediate succession, one right after the other. Whereas other words on the list, such as the word dog, is distributed across time. You'll see the word dog, and then you'll see some other words, and then the word dog will come back. The consistent finding across these studies that use word lists is that participants have stronger memory for the words distributed across time, like dog, relative to the words that are masked in time, like the word cat. We know from over 1,000 published studies that spaced learning promotes memory. It's a highly replicable phenomenon that's been studied across many time scales and many contexts. One of the primary reasons that spaced learning supports memory is actually that we're forgetting during the learning events. So let me briefly describe why this happens. So in between each spaced learning event, you'll forget information. And what that forgetting does is it makes it harder to retrieve what you've learned. But at subsequent learning events, what you'll do is you'll retrieve your prior information from memory, and the cognitive effort that you engage in remembering that information will then be translated into a slower forgetting for that information. In other words, by trying to remember and practicing that retrieval, you'll then have a slower forgetting rate in the future. And so by engaging in that retrieval practice across distributed learning events, you're actually slowing forgetting and promoting your memory. Now, researchers have for a long time now known that spaced learning promotes memory and that forgetting can be manipulated to promote memory. But this isn't true for all forms of memory. For example, researchers have questioned whether or not this process of forgetting is good for everything. And in particular, researchers have asked, can forgetting promote categorization and concept learning? And the categorization and concept learning is learning that things share similarities and differences in the world. So for example, a golden retriever is called a dog, and a wiener dog is also called a dog. Even though they look very different, they share similarities and thus belong to the category of dog. And general intuition would say, I don't know if forgetting is good, because in general, intuition tells us that forgetting is not good, that it's a bad thing. However, even researchers who are experts in this field have really argued that yes, forgetting should deter categorization and concept learning. And it's really fun to go back through the previous literature and read old studies, because there are some fighting words out there. People really had strong beliefs that forgetting would deter conceptual development. My favorite quote is from Ernie Rothkopf, where he argued that things like forgetting and spaced learning would be the friend of recall, so help us to remember, but the enemy of induction. So in other words, it would deter our ability to learn categories or in concepts where we have to abstract out across our experiences. Let me walk you through this argument. So imagine that you're a young child and you're learning about the category of bunny for the first time. You'll see one bunny in one context, and then you'll see another bunny in another context, and then you might see a third bunny in a different context. And what you need to do in order to learn the category of bunny is to abstract out the similarities and differences across these experiences. So you might see that, well, the bunnies share the same shape. And so maybe that's a relevant feature of the category bunny. However, there are other features that vary. So for instance, the color of the hair is different across these bunnies. And a child might think, I guess the hair color is not a relevant category. It's irrelevant to the category of bunny. And the reason that children need to abstract across these experiences is they have to know what to generalize based on when they see new bunnies that they've never seen before. They should generalize based on body shape rather than on something like the color of the hair. Now, Ernie and others thought that the forgetting would deter this process, because how are you supposed to abstract across all of your experiences if you can't remember your experiences? So for instance, if you can only remember the body shape of one bunny you've seen before, how are you supposed to know that body shape is a relevant feature to the category of bunny? You can't remember that all the bunnies shared the same body shape. Same thing goes for irrelevant features. If you only see one color of hair and you don't see that it varies across all the different bunnies, you might think that hair is a relevant feature. You know, the first bunny you see might be a certain color, and you would think that that color defines the category bunny when it does not. So in other words, forgetting should be bad for abstraction. Now, what's interesting is that despite these fighting words being out there and these strong held belief by researchers, no one had really tested it. So what we decided to do was to test this hypothesis. And one of the most common methodologies that we've used to test this hypothesis is called the Novel Category Induction Task. And this task is designed for young children who are learning words and categories for the first time. And what we do is we present them with novel objects and novel words to ensure that they're learning these objects and words for the first time. So just as an example, an experimenter might show children a series of novel objects like this and label them and say, this is a wug, this is a wug, and this is a wug. And then at a post-test, present children with a series of objects. Some they've never seen before, some they have. So for example, they've seen a cat before. And then it's the child's job to generalize the category that they just learned to a new instance of the category. So what the experimenter would say is, can you hand me the wug? And it would be the child's job to pick up that novel wug they haven't seen before that shares a similar feature, in this case, shape, to the objects that they saw during learning. So this is referred to as the novel category induction task. And today I'm going to show you two experiments, experiments 1 and 2. And the participants in these experiments were typically developing 2 to 2.5-year-old children. And again, we were really interested in how this process unfolds when it's organically unfolding a lot during development, which is the toddler period. They're learning lots of words and new categories during the toddler period. We made very simple manipulation on the classic paradigm. And what we did in experiment 1 is we presented children with novel words and objects on one of 3 schedules: simultaneous, masked, or space. I'm going to walk you through each of these presentation schedules now. In the simultaneous condition, children were presented with 4 objects at the same time. They were all put on the table simultaneously. What the experimenter would do would label each of the objects. So the experimenter would say, look, this is a wug, and point to the first object. They would wait 10 seconds and then point to the second object and say, look, this is a wug. Wait 10 seconds, and so on and so forth for all 4 objects. Now, in this condition, forgetting is minimized because all of the objects are present to the child at the same time, and they keep hearing the word wug over and over again. So children don't have to rely on their memory to abstract out what are the similarities and differences among the objects. They're all on the table at the same time. The second condition was the mask condition. And in this condition, we presented children with objects one at a time. So the experimenter would put an object on the table and say, look, this is a wug. Wait 10 seconds, take the object off the table, and then put it back on the table, or put another object on the table and say, look, this is a wug. Wait 10 seconds for the child to play with the toy, take it off, and then put a third object on, and so on and so forth. So in other words, the objects were presented one at a time. Now, in this case, children need to rely on their memory a little bit to remember what they've seen earlier. Because they only see one at a time, they have to think back, what were the colors and shapes of the objects that I saw earlier? The final condition was the space condition. In this condition, what children did is they also saw one object at a time, but instead of seeing them in immediate succession, like in the mask condition, there were 30-second delays between each presentation of the object. So what children would do is they'd see an object, the experimenter would put one on the table and say, look, this is a wug. And then the experimenter would take it away, and there'd be 30 seconds of irrelevant activities like playing Play-Doh, putting stickers on paper, anything to keep the kids at the table and entertained. After that 30-second play period, children would then be presented with another object, and the experimenter would say, look, this is a wug. And that would happen so on and so forth for 4 objects in total. Now, what you can see across these conditions is that the only thing that's being manipulated here is the timing. Either children see all objects simultaneously, preventing forgetting, or they see them one at a time. And what the space condition does is it introduces the most forgetting during learning. Because there are those 30-second intervals between each presentation, that gives children the opportunity to forget in between each object. And so they have to think harder and harder about what they saw earlier in order to abstract the relevant and irrelevant features of the category wug. Children were also presented with a distractor item during learning, and the experimenter did not label this. They would say, look at this toy, and it was presented for the same amount of time as the objects, 40 seconds. And then there was either an immediate test or a test after a delay, a 15-minute delay. And the reason for this difference across conditions is that we were interested not only forgetting during learning, like that's those 3 conditions I showed you earlier, but we were also interested in forgetting between learning and test. And so immediate condition prevents forgetting from happening between learning and test, and a 15-minute delay introduces the opportunity for forgetting between the immediate and delayed test. So we're introducing forgetting at different levels of the learning process. And then the test item was very similar to what I showed you earlier. Children would be presented with 4 objects, and then it was the child's job to pick out a novel instance of the category that they learned about. So the experimenter would say, "Can you hand me the wug?" And it's the child's job to pick up the wug and place it into the experimenter's hand. Okay, what I'm going to do is show you some results. And this is the results of experiment 1. And what you're seeing on the x-axis is the testing delay. So either children being tested immediately or a 15-minute delay. And then on the y-axis is the number of correct responses. So this is the mean number of times that children correctly handed the wug to the experimenter. So here's what we found at the immediate test. Children in the simultaneous condition significantly outperformed children in the masked and the spaced conditions. So if Ernie Rothkopf were here, he would say, "Look, I'm right. The condition that had the least amount of forgetting led to the most learning." Because the simultaneous condition at the immediate test introduced no learning or no forgetting during learning, but also no forgetting between learning and test. So this would sort of prove Ernie and others right, that forgetting does deter conceptual development. However, let's look at the data from the 15-minute delay. What we observed at the 15-minute delay is that children in the space condition significantly outperformed children in the simultaneous and mass conditions. And you might wonder here, well, wow, this is an interaction, a completely different pattern of results at the delayed test. And indeed, what we see here is children that had the most opportunities of forgetting performed the highest. Because indeed, the 15-minute delay was the most amount of forgetting between learning and test. And then the space condition introduced forgetting during the learning process. So this is the exact opposite of what Ernie would predict. Here, what we see is that forgetting might be facilitating abstraction and generalization. I'm going to jump to experiment 2 quickly and just explain why we did experiment 2. So in experiment 2, what we were interested in is we said, well, we think that forgetting is happening between learning events. In other words, we think that these 30-second gaps introduce opportunities for children to forget. But what we wanted to know is we wanted to have data to actually show that the forgetting is happening. So what we decided to do in experiment 2 is ask children to retrieve their learning during learning. And here's how we did this. So imagine children are in the simultaneous condition. They'd have 4 objects put on the table at the same time. And the experimenter would label the first object and say, look, this is a wug. Wait 10 seconds and then point to the second object and say, what is this called? They would wait 5 seconds, and then regardless of what the children said, the experimenter would say, this is a wug. And then they'd move on to the third object and they'd point to it and they'd say, what is this called? They'd wait 5 seconds, and then regardless of what the child said, they'd say, this is a wug. And they did that for all 4 objects. The same thing happened in the masked and the space condition. Children would hear this is a wug on the first presentation, and then on the subsequent presentations, the experimenter would first prompt the children to report the word by saying, what is this called? Wait 5 seconds, and then say, this is a wug. And what these retrievals did is it gave us a sense of how readily children are retrieving information during learning. And what we predicted is that children in the space learning condition would demonstrate the most forgetting because of those 30-second intervals. Okay, here's some data comparing the final test from experiment 1 and experiment 2. And what you can see is we observe the same pattern of results across experiments. The bars are a little bit higher in experiment 2. This is to be expected. It's because children are getting more retrieval practice by us asking them, what is this called? And so they overall did better. It's basically a retrieval practice effect here. But we see the same pattern, that at the immediate test, children do better in the simultaneous condition, but at the delayed test, they do better in the space condition. Here, what you're going to see are 3 bars representing overall retrieval successes in the simultaneous masked and spaced conditions. So that's what will be on the x-axis. And then on the y-axis, what you'll see is the mean number of retrieval successes out of 24. So there were 8 trials with 3 retrieval attempts on each. So that adds up to 24. Here's what we found. We found that children in the simultaneous condition had significantly higher performance than children in the mass condition. And we found that children in the mass condition had significantly higher performance than children in the spaced condition. And this is exactly what we predicted. Children in the simultaneous condition are having a lot easier time retrieving the label for the category because they're not experiencing the same degree of forgetting as children in the masked or spaced conditions. And indeed, children in the spaced condition are struggling the most. We took this same data and we plotted it by time. And just as a reminder, what we did is we had retrieval 1 be at the second learning event, retrieval 2 was at the third learning event, and retrieval 3 was at the fourth learning event. Because on that first learning event, we labeled the object. We said, this is a WUG, and then asked them what it was called on each subsequent learning event. So on the x-axis, what you're seeing here is retrieval attempt 1, 2, 3, which corresponds to learning 2, 3, and 4. And we wanted to know if the nature of retrieval changed across the learning phase. So what you're seeing here first is performance for the simultaneous condition. And what you see is a relatively flat line across the 3 retrieval attempts. And what this suggests is that children in the simultaneous condition are observing overall high performance that doesn't change much across the learning phase. The next line that you're seeing is performance in the mass condition. It's a similar pattern to children in the simultaneous condition. It's just lower. So it's a little bit harder, but there's no change during learning for children in the mass condition. However, we see something fundamentally different in the space condition. What we observe is that the first retrieval attempt, children really struggle to retrieve information. In fact, it's not significantly different than 0. So essentially, when children get to that second retrieval attempt, they kind of stare at the experimenter and they don't know what to say. They're unable to produce the word WUG. However, across the learning phase, we observe performance. So they get better and better at retrieving the word WUG during learning. So what this data does is it confirms our hypothesis that this paradigm does introduce different levels of forgetting during learning. But what this data also does is it provides evidence for a theoretical account that explains why forgetting is promoting learning. And what we have argued is that forgetting is a form of abstraction. Forgetting acts as abstraction in order to promote conceptual development. So I want to walk you through now how this works. So imagine that you're a child and you're seeing a WUG or a new toy for the first time. Well, you're going to see that WUG and you're immediately going to forget everything about that WUG according to the curvilinear pattern that I showed you earlier. And here what we see is that forgetting curve. So you'll see your WUG and a certain amount of time will go on and you will then experience another WUG or another new toy that shares the category label. And what will happen is that that new WUG will prompt you to recollect information that is similar to the information that you saw earlier. So in this case, what is similar across these 2 items is their shape. And so what you'll do is you'll retrieve the shape that you saw earlier, and you'll engage in cognitive effort doing so because you've forgotten about it. And so you have to dig through your mind to find that information, that past memory. And what that cognitive effort does is it slows the memory for shape, which in this category is the relevant feature. Now, that second object won't cue you to recall other types of information, like the color or the texture of the object that you saw earlier, because there isn't a match across the items. And so what that means is that you'll continue to forget that irrelevant information, the texture and the color, at the same rate as earlier when you first saw the original WUG. And what you can see from looking at this image is now there's different forgetting rates for information that's relevant and information that's irrelevant. Let's do another demonstration of this. So let's just say that more time goes on and a child then sees yet another WUG. And what that third WUG is going to do is prompt children to recall information from the first and second WUG that's similar to that item. And again, that similar feature is shape. And so what children will do is they'll engage in cognitive effort, searching for that shape information. And what that cognitive effort will translate into is a slowed forgetting for that feature, shape. So it's again slowing the forgetting. However, features like color and texture are continuing to be forgot according to that original forgetting curve. So they're being forgotten at a much different rate than the relevant information. And what we hypothesize happens across early development or learning about something new for the first time is this process of where we continually retrieve relevant information in the world, and then we don't retrieve irrelevant information in the world. And as this process happens over and over and over again, we end up with different forgetting curves for information that's relevant and information that's irrelevant. And so by the time children or adults need to generalize to something new in that category, they will more readily retrieve relevant information like shape compared to irrelevant information like color and texture. And this will support generalization and conceptual development because they're retrieving what's important and then applying it to that new category. So in other words, it's helping children, adults, everyone to abstract what's relevant in the world, and therefore helping us to learn categories and concepts. Just as a quick summary, for a long time, going back to the 1800s, researchers and general intuition told us that forgetting should deter conceptual development. It should prevent us from abstracting what's relevant and irrelevant in the world. However, my lab's work has shown the opposite, that forgetting can actually act as a form of abstraction, speed up abstraction, and help us to learn new categories and concepts. And so, while we've always agreed that forgetting can help learning and memory, we now know that it can help us think and develop our most higher order forms of learning, like learning a new language or learning complex concepts. So that's the silver lining, is that even though forgetting is inevitable and predictable and will prevent us from remembering information, it's also going to help us. It's going to help us remember what's important so that we can generalize across our experiences based on the important information. So I have a number of concluding thoughts that I'd like to share with you all. The first concluding thought is to share some of the exciting work that we're doing, trying to build off this basic research to design interventions for children. One of the things that we've done is we've thought, well, why don't we integrate forgetting into curriculum? In other words, we should work with teachers and parents in order to get them to encourage their children to forget. Now, I know this sounds very counterintuitive because, wow, teachers are trying to help kids remember, parents are trying to help kids remember. But remember, forgetting can help us to remember. So what we've been doing is we've been working with classrooms and teachers and helping teachers to integrate spaced learning into their curriculum. Here's a quick example. In a lot of early childhood curriculum, teachers use units. So they might have a lion month or a flower month where they talk about the same thing in extensive conversation for a month and then move on. So in other words, it's an immediate succession. It's kind of like cramming. So instead, what we've done is we've encouraged teachers to distribute lessons out across time. We've done a series of experiments to provide empirical evidence for teachers that this is a good thing to do. So for example, in some of our studies, we come up with different learning schedules for science curriculum. And the example that I'm going to show here is the context of children's science curriculum about food chains. And food chains are a perfect context because what teachers do is they introduce food chains across different biomes. So they'll introduce the food chain in the grasslands and then the desert. And then what they expect children to do is to abstract out across all these different biomes in order to generalize to a new biome like the Arctic or the swamp. And so what we do is we work with classrooms and teachers and develop a schedule, such as the schedule you see here, where there's one of three presentations options. There's a massed schedule, a clumped schedule, and a spaced schedule. What you'll see in the mass schedule is that lessons about food chains are presented in immediate succession, just like we do in the lab with the word lists. The spaced condition distributes all the lessons out across days of the week. So there's time in between each lesson, which maps onto the space schedules that we use in the lab as well. In these studies, we use an intermediate condition called the clump condition, which introduces a combination of massing and spacing. So some of the lessons are presented in immediate succession, whereas other lessons are distributed across time. And we have each lesson be about the same amount of time so that we control for time across these experiments. And we have a test for children that happens 1 week after their last lesson to understand what they remember from the varied conditions. And I'm going to show you some data here where we had two different types of tests, a simple generalization or simple concepts. This is things like learning that bigger creatures typically eat smaller creatures. And then we also had some complex concepts. And the idea that we tested here was the idea of interdependence. So in other words, if something happens to a particular creature in a biome, it affects all the other creatures. So for example, if there are no more fish in the ocean to eat, that affects all the other creatures that live in the ocean. They will have less to eat because there are no more fish, especially creatures higher up on the food chain. So that's what you're going to see on the x-axis. On the y-axis, what you're going to see is the difference between the pre-test and the post-test. So we gave the test before learning and after learning. And what you'll see is for the simple generalization or the simple concept, we found that children in the space conditions significantly outperformed children in the massed and the clumped conditions. And this is what we expected from prior research. We expected to see this based off of the relatively simple categories like the WUGs that you saw earlier. In this work, it was actually our first time testing whether or not we would find this phenomenon in a more complex task, like learning about interdependence. But let me show you the results. Here they are. We found the same pattern. We found that children in the space condition significantly outperformed children in the clumped and massed conditions. So what these classroom-based studies do is they help teachers to understand how they can manipulate forgetting by using space learning in their curriculum and in their teaching practices. And indeed, it's been a real joy for us to work one-on-one with teachers in classrooms to help improve STEM learning by just making these simple changes. It's amazing how just small changes in the timing of the lessons can create more learning in the classroom. And indeed, this is a free, innovative way to improve education. And we're actively studying how to develop these types of interventions so that we can encourage forgetting in the classroom and encourage teachers to think about how they can encourage forgetting in their students. So this is just an active area of research and is, to be determined how much more we can do with this. We, in another year or two, please contact me and we'll have more information about how the curriculum and the interventions are going. Another concluding thought that I really wanted to share with you today is how researchers are actively studying forgetting in the current times, namely during the COVID-19 pandemic. And if you're like me, you may have noticed, particularly during the lockdown period, that your thinking and learning have changed during the pandemic, and in particular, that you've forgotten faster than you normally do. So you might lose your keys, you might not know what you had for lunch, you're forgetting things that you normally wouldn't forget. And there's a number of reasons of why you are experiencing that faster forgetting. Here's a quick summary of what research has found. So first, we know that there are routine changes. You're not going into the office, you're not going to the gym. And the reason that that affects our memory is that our routines serve as memory cues. We learn where we always put our keys when we go to the office, where we put our lunch, who we talk to and have chit chat with in the hallway. And when we lose that routine, we lose the cues. And so what that's doing is it's speeding up forgetting. If we don't have the cues, we're not going to remember, and we're going to continue to forget according to that faster rate. The second reason that we observe faster forgetting during the pandemic has to do with a lack of social interaction. Social interaction is important for so many reasons, and I want to highlight two now. So during the pandemic, you haven't spent as much time with people, and people also serve as memory cues. They prompt you to talk about your past. So just imagine that you're chatting with a friend or a family member. They might say, "So what'd you do last week?" And you would respond with, "Well, I got to talk to some friends. I spent some time. It was so much fun." And what you're doing by having that conversation is you're recollecting your past experiences and sharing them with that other person. And so when people aren't around to prompt you, you're not engaging as much practice in retrieving the past. And again, that contributes to how fast you forget. The other reason that social partners are so important for our memory is that they contribute to our emotional well-being. And we know from a long history of research on emotions and memory is that when we're experiencing more volatile emotional experiences and when we're sort of experiencing more negative life events, that we actually forget faster during those times. And so for those of you who are really missing being with other people, and are just sort of having a case of the blues, you're forgetting faster, maybe because of your current emotional state or the emotional state that you experienced, particularly during the lockdown when you had little to no social interaction with people. So there are many reasons that our social partners are particularly important for our memory. The third reason that we think people are forgetting faster during the pandemic is that we're engaging in more behaviors that speed up forgetting. And one of those behaviors is alcohol consumption. So there's a lot of research showing that during the last 18 months, people have been drinking more alcohol and engaging in more drug use than they did prior to the pandemic. And we know from research on alcohol and drugs that they act as a memory destabilizer and therefore cause faster forgetting. So if you're engaging in an overconsumption of these substances, that can lead to complete memory loss. Not only are you forgetting faster, but you might not have any access to memories from those states of overconsumption. So certainly we think that a lot of the forgetting that's happening because of the pandemic is because people are choosing to engage in behaviors that are negative, that they, for memory at least, that they didn't before. The last reason is that many of us during the pandemic had lifestyle changes. And one of the big lifestyle changes is that many of us exercised less. And this is even despite the public service announcements in the news encouraging people to get out there and go on a walk, be outside, exercise. And one of the reasons for that public service announcement, or why it was in the news all the time, is that we know that exercise is so valuable for so many things: our physical health, our mental health, and the rate at which we forget information. We have a long, sort of big body of work showing that for those of us who engage in more cardiovascular exercise, but exercise more generally too, that we are more, we're more readily able to retrieve important information when we need to. So in other words, exercise is good and supports our ability to retrieve information. And so because of that, we are forgetting faster if we're exercising less. So in brief, there's a lot of lifestyle changes that we made that aren't for the benefit of our memories. And that's yet another reason why we might be forgetting faster. And researchers are actively studying, now that we're coming out of the pandemic, how our forgetting is changing. We expect that once we establish those new routines, live a healthier lifestyle, that our forgetting will slow and go back to be what it was pre-pandemic. But we're also concerned that a small group of individuals might not make those changes, might continue to experience negative effects of the pandemic and thus have faster forgetting. And so researchers are actively trying to figure out how we can identify those individuals so that we can help them. My final concluding thought is just to say that we don't know why we forget. And we are actively studying it now. But we do know that forgetting is essential for our lives. Forgetting can help us to remember. It can help us to learn new things like new words and concepts. but most importantly, it can define who we are. If we think back to the pandemic, there's a lot of things that we probably want to forget, right? We had a lot of negative experiences, particularly during the lockdown period. And that forgetting is good. So even though you may have forgotten faster during the pandemic and forgotten a lot of the things that happened to you, I would argue that that's a good thing. What your mind and brain are doing is they're abstracting out what's important to remember. Hopefully the good things and the parts of yourself that were able to endure during the pandemic. And I'm hoping for all of you that you have a stronger sense of self and know more about how you can endure in tough situations. And forgetting is going to help you do that. Okay, it's going to help you to remember when you were strong. So on that note, I just want to say forgetting, although intuitively may seem like a bad thing, is a great thing. And it's helping you with all facets of your life. Thank you so much for listening. Please feel free to reach out if you have questions about forgetting. As I mentioned at the beginning of the talk, I spend lots of time thinking and learning about thinking and learning, and I would love to do that with you as well. Good evening.